name is Banu. Today I am going to discuss about the topic of concept of random process in probability theory and stochastic process. Introduction to random process. In earlier chapters we have studied probability theory, how to deal with uncertainty, and random variables whose values are not fixed but depends on chances. Now we move to random variables to random process, which in a random process consists of different types of random variables like x, y, and so on. Definition of random process. A random process is a time varying random phenomena described statistical using capital PDF probability distribution function, small PDF which is probability density function, correlation and covariance, which helps us to understand and model signals such as noise and message signals in communication system. What is a random process? A random process is also called as a stochastic process. It is collection of random variables that changes with time. In simple terms, it is a time varying random process. Examples of random process are message signals in communication, background noise in a receiver, variation in weather, speech or music signals. By this, we can say that random process is a time is changes with respect to time, and it varies its signals amplitude as time goes on increasing or decreasing. Why do we use random process? We use random process to study signals that change unpredictably with time, such as noise or message signals. We cannot fully know the behavior. Only their statistical properties like average, power, variance, etc. can be known. Hence, they are described statistically, not deterministically. Yes, we can prove random process by using power, variance, etc. like statistical properties, mean, and so on, but not by using deterministic properties. Next, statistical description. Because the exact values of every moment are unknown, we describe the process using statistical measures such as probability distribution function, probability density function. Distribution gives the probability of different values, and whereas density describes how these probabilities are distributed. These functions tells us everything about the randomness or statistical behavior of the signal. Means these are some statistical descriptions about random process. Next, energy and correlation. Random process have infinite energy because they exist over a long time. So instead of calculating total energy for overall periods, we take a small finite energy functions. We perform operations to that energy functions, and for whole the process, like for whole signal, the small consists of same properties and same energy, same everything, and with respect to of other also it will be same, repeated same. So we consider a small part in that function, and we perform the operations. Like correlation function measures how similar signal is to itself at different times. Covariance functions measure how two random signals are varied together. These helps us understand the time domain behavior of random process. Random process temporal characteristics mean this is the actual definition of random process. A random process is also a stochastic process, as you know, is a process in which a random variables depends on both time, space. Time, how the variable changes over time. Sample space is the random outcomes for an experiment. So a random process is written as capital X of S comma t, or simply X of t. Here S represents the randomness sample point, t represents the time. That means for every random outcome S, we get a different signal, function, or time. Different forms of random process. When t is fixed, you only look at particular instant of time. The random process becomes random variables because only randomness remains, represents as x of s comma t1. Here t1 shows the number of intervals, like same fixed interval of time t. At the particular interval only t1. This shows the random value of the process at time t1, and x is a sample space as it's varying with respect to the signal, but time t is fixed. When sample space S is fixed, you are looking at particular outcome, one experiment. It becomes a real function of time, represented as x of s1 comma t. This means for one specific experiment s1 how the signal changes over time. Example, waveform of a realization of random signal. Previously we have seen that here time is fixed, so we consider as x of s comma t1. Here sample space is fixed, so we written as x of s1 comma t. Here time changes, but the sample space is remains constant. In next condition, we can observe that both time and sample space are fixed. Both are given specific values, so it becomes a constant represented as x of s1 comma t1. Example, the value of an experiment at specific instant in one experiment. This gives like uh, getting a specific instant of time at specific value. Here the experiment is also fixed and also the time is also fixed. Like we have checked that time is fixed, sample space is fixed, and both fixed conditions representation nature. Example, representation of time variable sample space variable are x of s comma t, our general representation of random process. Time is fixed x of s comma t1, sample space fixed x of s1 comma t, both fixed x of s1 comma t1. Nature random process, random variable, time function and constant. Example of time variable sample space variable are random signal, time fixed as noise as particular instant, sample fixed one noise waveform, both fixed single value of signal. Next, classification of random process. Based on whether time and random variable are continuous or discrete, we classify random process into four types: continuous random process, discrete random process, continuous random sequence, discrete random sequence. Here, in continuous random process, time variable is continuous and random process variable is also continuous. In discrete random process, time variable is discrete and random variable is continuous. In continuous random process, time variable is continuous and random variable is discrete. In discrete random sequence, we can observe that time variable discrete and random variable is also discrete. In continuous random sequence, we can observe that time variable is continuous and random variable is discrete. And here are some examples of continuous random process, discrete and continuous random sequence and discrete random sequence. You can go through them. Next, classification of random process are classified into four types as we seen: continuous random process, discrete random process, continuous random sequence, and discrete random sequence. Now let us come to the first one, continuous random process. A random process is said to be continuous if both time and random variable are constant over the entire duration. In this type, the random variable can take any value within the continuous range for all moments of time. An example is fluctuation of noise voltage in an electric circuit when both time and amplitude vary constantly, continuously. Sorry. Yeah, here we can observe the graph, like observe the figure. Sample function of continuous random variable time t is uh, here in continuous random process. Here both uh, continuous in both time and random variable. So the figure we can observe the plot is like random. It's changing with respect to time. We can't observe same pattern at any interval of time. The patterns are not similar, and the amplitudes are also changing, varying continuously with different values. So here in continuous random process, we can say that both uh, time and random variable are continuous over entire duration. Next, discrete random process. In discrete random process, the random variable takes discrete values, but time is continuous. The random variable can switch only between certain fixed levels while the time progresses continuously. For example, a digital signal that alternates between two discrete levels, such as positive and a negative level, but exists continuously in time. As we can see, the time is varying with respect, the signal is varying with respect to time, but the sample is either 0 or 1. Like either if we consider upper above as minus 1 and lower one as minus 1, then we can observe that it's fluctuating from minus 1 to 1. Either we can observe sharp edges also, like sharp falls and sharp rise, as a as similar to a rectangular signal. So next, continuous random sequence. A continuous random sequence occurs when time is discrete. Here time is discrete but random variable is continuous. In previous case we checked that both time is uh, time is discrete but time is continuous and random variable is discrete. Like similarly here, time is discrete but random variable is continuous. The random signal is defined at specific in time intervals, but its amplitude can take any continuous values. It is represented as a set of random variables defined only for discrete sampling instance, such as tk is equals to 0 comma 1 comma 2 and so on. This type is often used when sampling a continuous signal without quantizing its amplitude. Here the time is discrete but the random variable is continuous. As we can see, the waveform sample function of a continuous random sequence is changing with respect to time, changing with respect to time. So in discrete, yeah, we can draw the waveform to, we have drawn the join the points and waveforms, we can go through them. Here in continuous random sequence, time is discrete but random variable is continuous. Next, in discrete random sequence, in discrete random sequence, both time and random variables are discrete. Here, both the time and random variable are discrete. The signal is sampled at discrete time intervals, and the amplitude is also quantized into discrete levels. Here, the signal is sampled at discrete time intervals, and amplitude is also quantified into discrete intervals. The process is commonly used in digital signal processing, which is known as DSP. The amplitude may be represented using two levels or multi-level quantization depending on the application. It is often obtained by both sampling, discretizing time, and quantization, discretizing amplitude. Here, the time is discrete, and also the sample space is, random variables are also discrete. We can observe the graph waveform like this. Yeah, that's all.